cool. So I think what I wanted to get down today is basically Tensor Network. So installing Google Tensor Networks. I've been watching a really cool video, like the introduction that was done. I don't know if it's in here. So definitely, if I go to YouTube, I think I'll find these. I don't know what is YouTube. What is this? YouTube.com. Let me see if I can find this. Do I have an account like that? Yeah. So I've been watching Tensor Network. This video by Chase Roberts. It's probably all you need. Definitely watch that. Let's see if I can put it in the link in the description of the video. Definitely watch that. How do I get this installed? Install Tensor. So I'm gonna open another. I'm gonna open another shell. Workspace, and then I'll go to for optimization, pip3 install. What's the Tensor Network? Cool. Basic API tutorial, basic example. Let's see. Cool, it's installing. Because what I want to do now is I want to just play with this a little bit and see if I can get like something running. So we've got the here we've got the Cubo, and we played with these. Now I have this cube, and I want to know what I can do with these. Can I do the decomposition of these, and how can I find the eigenvalue? Because that's what we want to do. We want to at the end essentially find the eigenvalue, right? Cell below. Because that's trash. So this is going to be basically Tensor Network stuff that I'm playing with here. So NumPy is imported. I want to import Tensor Network SDN here and then just play with this. Has this been installed yet? No, installing still. Oh, successfully installed. Okay, cool. I'm not so sure if I don't need to rerun these though. First of all, I probably need to. Why don't I just import this there? Yeah, I think I should restart the kernel, to be honest though. Because I don't think that this is kernel restart. I think I should restart that. Because I just freshly installed these. So, and I think I keep reading the MPS all over the place. And Tensor Network, MPS, finding lowest eigenvalue. What's the method here? Look at this. So here's a PDF where they talk about these. Eigenvalue. Introduction, the smallest. Ground states, approximation by matrix product state. So this is what we want. The matrix product state formalism goes back to several sources, including their revival, while a more recent treatment is due to Vidal. The application to the eigenvalue problem was discussed by Delgado et al. In 36. A similar independent line of thought resorts to the fact that density matrix renormalization group methods as developed by Wilson and White have a natural interpretation as optimization in the class of MPS states. As has been mentioned already, ground states of gapped 1D Hamiltonians are faithfully represented by MPS. Where the MPS approximation can be computed efficiently, the rationale being an area low. Okay, I have no idea. So this is working again. Tensor network, no module name tensor network. Warning, blah blah blah. Successfully installed and tensor network. Okay, so why is it not recognizing it? Should I? Should I restart the whole thing? No, what is it doing? Microsoft Store? What the heck? I just wanna... How can I just open, like, whatever console interface of Python? No. I don't want to write one, I want to... Whatever. Do I have to just close these and start again? I mean, I restarted the kernel, but that should be enough, but let's just... Whatever. So, I'm going to be going to... Okay, I'm here already, so Jupyter Notebook. Let's see if starting that again works. And we'll go here, and we will run this. Let's see if it complains. It complains. No module named Tensor Network. But it installed, right? Maybe it has another name? Any issue with the Docker setup? No. TensorFlow, no, Tensor Network. Yeah, I installed Tensor Network. I don't like that. Anaconda 3. Maybe I should use Peep, not Peep 3. It's worked before. I don't know why though. We should be using the 3, right? I don't know. But let's see. Yeah, all satisfied. Now it's installing the thing. It's Python 3. Yeah, what's wrong? Successfully installed. Cool, and now if I just restart the kernel and how do I know what's the status of the kernel? Kernel idle. Restarting kernel. Okay. Refresh. I hope this works now. Otherwise, otherwise I have to leave the video here because it's really short. Because I don't have much time left. What is it doing? Why is it thinking still? Waiting for localhost? What are you doing? This is reloading. I don't know why it's so slow. Okay, now we're there. Now, I hope it works. I really hope it works. That's, yes, okay, I don't know why. Whatever, so we're doing these, we're getting that, and now we're getting the, no, I didn't want to run, no, oh crap, I'm wasting my credits. Anyway, let's do these, does this work? Yes, we got a 10, that works. Okay, now, what happens if Cubo is the matrix, right? So can I just like give it Cubo? Cubo, can I do that? Well, it doesn't print 10, obviously. But what does it print? Okay, you're connecting, oh, and then you're contracting the edge. Can you do stuff like that? Yeah, you can do cool things. Okay, cool. So you can do these. I don't know exactly what I'm doing, but there, I'm contracting stuff. But now the question is, cool, I have a Cubo. And now what? Like I thought, I think so you could in theory split node. Yeah, split node. This will return two nodes and a tensor of the truncation error. The two nodes are the unitary matrices multiplied by the square root of the singular values. The left edges are split node full SVD. If you want the singular values in its own node, you can use split node. Psych root. So this somehow splits. Okay, I installed that, but I need to find what's the way, like how to solve the application drag value problem was discussed by Delgado et al. Maybe I should just use the multiverse computing paper actually for these. And try to get like where tensor networks. Tensor networks. People have been using them as an answer to approximate the low energy states of Hamiltonians, and many algorithms have been invented to this aim. Example, reference 19. The idea here is that by mapping optimization problems and Hamiltonian eigenvalue problems, yeah, okay. In our case, we implemented an optimization strategy over the so-called matrix product states. Reference 20. These how many of the states have been tested already in variety. So it's reference 20 and 19. So I should go and take a look at these. So this is one paper, and this is the other paper. Finitely correlated states on quantum spin chains. Can I find this somewhere where I can actually read it and not pay for it? Because that would be bad. That would be bad. Tensor networks are complex quantum systems. I think this one should be available in the archive. Yeah. Because I think I've seen this before. Eigenvalue. Lee and Haldane pointed out that the eigenvalues of the reduced density matrix of a B partition codify important information about the boundaries of the system. That's not the word that I want. The eigenvalues of ρ define the eigenvalues of the Hamiltonian, which can be grouped according to quantum numbers, such as the vertical momentum. So P epsilon a cylinder to compute entanglement Hamiltonian. It's the entanglement Hamiltonian. One makes a B partition of the system. It's going to be a tricky thing to do, though. Spectral eigenvalues of agent. MPS. I was hoping to actually find directly an algorithm, but it seems like I'll really have to dig deep into these. Eigenvalues of Hamiltonian MPS tensor networks. Tensor networks. Tensor network methods in many-body physics. Algorithms based on MPS are extremely successful in approximating ground state. Okay, this is what I want to know, though. Ground state. Tensors can present ground states of local Hamiltonians. But how good is his position? This question is fundamental importance. This version algorithms based on tensor networks can only perform well. Variational algorithms based on tensor networks can only perform well if any ground state can be approximated efficiently in such a way. While any state can be written as a tensor network state, the number of parameters needed for the description might be too large. Algorithms based on MPS are extremely successful in approximating ground states of one-dimensional many-body systems. In 2 dimensions, algorithms based on PEPs are more difficult to implement but have been gaining popularity in recent years. One-dimensional. What does it mean in this case, one-dimensional, though? One-dimensional many-body systems. Many-body systems. Before introducing tensor networks, spin lattice models. Wow. Oh. This is gonna get deeper and deeper, and bigger, the rabbit hole. Like, they don't really quote anything special, right? They just say, hey, we do this with matrix product states. Matrix algorithm simulating the ground state. We quantify how well matrix product states approximate exact ground states. Maybe here. It's going to be something. It's 2005. That's really old, but maybe. A polynomial time algorithm for ground state. Okay, maybe this is something we could implement. NPS. Okay, so there's an Qt NPS, the algorithm. The problem of finding an approximation to the ground state can be expressed as a convex optimization problem of finding the minimum trace subject where this is an n-qubit density matrix describing the state. As the dimension of the scales of the matrix scales exponentially in n, solving this complex problem generically requires exponential time. Oh, so it's about the trace. So if you find the trace, so finding the trace is the ground state. Is the trace of density matrix. Is this the ground state? Ground state. That feels like hopping through ground state. No eigenvalues. Let's assume that a complete density operator for a pure ensemble that is with the rho being one of its eigenvalues. And somehow the matrix is always equal to its trace. Is equal to 1. Okay. So it seems it's got to do with the trace, which then makes sense. So you then the driving idea behind the algorithm is to progressively construct in a single left-right pass a basis for a subspace of polynomial dimension of the whole subspace guaranteed to contain a suitable approximation of the ground state. Solving this complex program generically requires exponential time. The driving idea behind our algorithm is to progressively construct in a single left-right pass a basis for a subspace, blah blah blah. This contrasts strongly with the usual approach taken by the MRG of performing multiple passes of local optimization with no guarantee of the quality of the approximation. Wow. What is the algorithm? Okay, the left half MPS, so it's doing the boundary contractions. It's kind of contracting stuff step by step. Okay, but that's something at least. That's definitely something. The goal of the second step is trimming to reduce the cardinality of S to create a smaller set. To achieve these run. so I guess what I'll have to do is somehow take that matrix, split it, like what, the cubo? Like, do I just split the cubo? Like, is it the cubo? That's the problem. Like, what's the... I don't even know where to start. Because they literally don't mention a lot of things in here. So I need to... I don't think it's the cubo what I need, to be honest. That's the problem. But I need to get a matrix, and I need to basically... What do I need to do? So I need to build an MPS network and then try to calculate the trace. I don't know. Iteratively. I don't know. It's getting too late. It's definitely too late. Yeah, I'm gonna leave it here. That's a short video. I opened. I think that's okay. But it's always important, I think, to dig down to the very end of this. Nasty. So what is? Oh, any wave function of the system can be described inefficiently just by giving its coefficients in a computational basis. As such, this coefficient is understood as a tensor with n indices. Network of interconnected tensors. Interconnected indices are in the network are also called bond indices and provide the structure of the many-body entanglement in the quantum state. As is well known in physics, DNs are a natural tool to solve optimization problems. Reference 19. So many algorithms have been invented to this aim. Reference 19 and therein. And so this is reference 19, right? And I gotta find these here somehow. So I'm gonna have to dig into these. Is this reference 19? Too many things open. Reference 19. I think that's, sorry. Let's just follow the link. Yeah, that's it. Okay. Tensor networks. I just want to read 57 pages. I want to find the algorithm, but it's going to be complicated. Yeah. Awesome. That's going to be a lot of fun. A lot of fun.